Hello everyone. In this video we're going to prove this theorem. The theorem's set up on a scope line that has no primary assumptions. That's the way theorems are. And what I'd like you to do is grab a paper and pencil, hit pause on this video, and come up with some ideas, maybe even work the whole thing if you can, and resume the video when you're ready to proceed. Okay, so if we look at this theorem, the main connective here is our conditional, our horseshoe. I want you to make sure you look at the whole thing and make sure you understand that the horseshoe is the main logical operator. Once we know that that's the main logical operator, a strategy suggests itself, and that is that we should prove this using the inference rule conditional introduction. It's a rule that gives us as output sentences whose main connectives are horseshoes, so it's a good rule to use in this case. Let's go ahead and set up the subderivation since conditional introduction is a subderivation rule. Here we have our scope line, and we add the antecedent of our conditional, the conditional we want, to the subderivation's auxiliary assumption. So for all x, there's an x, there's a y, so for all x, fx, and there's a y, g, y. That's our assumption for conditional introduction. The very last line of conditional proof, subderivation is the consequent of the conditional we are after. And that, in this case, it's there's an x, fx, ampersand, gx. That's just the consequent of the conditional we're after. So let's think now about, well, let you pause and think now about how we might go about getting this new target sentence, this existential generalization. One good way of getting this existential generalization is actually by existential elimination. We don't have an existential generalization to apply existential elimination to, but it's sitting right up there on line 1. So we'll break it off. There's an x, there's a y, gy is the right-hand conjunct on line 1. So we get that by conjunction elimination on line 1. That gives us input for existential elimination, but we need to set up a subderivation. Okay, so there's our scope lines for our application of existential elimination. I want us to think about what we're going to have in the assumption for this subderivation. It has to be an instance of the existential we're working on. So we have to select a name new to the proof. There are no names thus far, so we can choose any name we want. This will be our assumption for existential elimination. Our assumption is an instance, a substitution instance of the existential on line 2. What's our target? Well, the last line is the sentence we want exported, and that's there's an x, fx, ampersand, gx. Okay? At this point, we can continue with goal assessment. That would be fine. I don't think it's particularly necessary or helpful in this case. It's also possible to just start moving down our proof by looking at rules we have an opportunity to apply. So we've already broken off the right-hand conjunct from line 1. Let's break off the left hand. For all x, fx. That comes from line 1, conjunction elimination. And then what we'll do is instantiate that universal generalization. So on line 5, drop the quantifier, replace the variable with the name a. Line 4, universal elimination. We can choose any name we want, but strategically we want the same name following these two one-place predicates, g and f. So that's why I instantiated to the name a here. Again, no restrictions on the names used in universal elimination. It's an easy rule to apply. What we're going to do on line 6 then, hopefully you'll have anticipated this, is we're going to conjoin lines 3 and 5. So we've got FA on line 5, got GA on line 3. So 3 and 5 conjunction introduction give us FA ampersand GA. Then we're pretty much right there. So we take line 6 as input for existential introduction. That gives us our target sentence. We replace the names A with the variable X, and we add the existential quantifier, making sure that we add the grouping indicators to give it full scope. It does have to be the main logical operator in the output of the inference rule existential introduction. Then we're pretty much home free. We have to complete our annotation. The application of existential elimination comes from the existential on line 2, together with the subderivation that started on line 3 and ended on line 7. So we got to complete that annotation there. And then our application of conditional introduction started way up there on line 1 when we assumed the antecedent of the conditional of the antecedent of our theorem. And then it ends on line 8 where we have the consequent of the theorem. That's conditional introduction. And there we have a nice little proof of a theorem.